In lesson 11.5 and 11.6, we're going to be looking at what happens when we have proportional shapes and we look at their areas and volumes. So how are their areas and volumes related if the shapes themselves are proportional? That's what we're going to investigate. So for our warm-up, we want to use algebra to express the area of the rectangle. So the area of the rectangle is base times height. But in this case, our base is 3L and our height is L. And combining that algebraically, this rectangle has an area of 3L squared. So then the question I'm going to ask you below is, if we had a rectangle similar to the first one using a scale factor of 2, what would our new length and width be, and what would our new area be? And how does this compare to the original area? So let's answer those. So our new length would be twice the old, our new base. So it would be 2 times 3L, which is going to be 6L. And our new width would be 2 times L, which again is just 2L. So our new base is 6L. Our new height is 2L. So then our new area, base times height, is 6L times 2L, which is 12L squared. So how does this compare to the original? So the original was 3L squared, the new one is 12L squared. So if we think of 12L squared over 3L squared, the L squareds will simplify, and 12 divided by 3 is 4. So the new area is 4 times bigger. So let's just think about this a little bit more, and then we're going to really unpack it. So this, remember, was a scale factor of 2. So this was a 1:2 ratio. And then our areas was a 1, I guess you really can't see that, huh? The area ratios ended up being a 1:4 ratio. This was the area, this was the side length. So I want you to keep that in mind, see if you can find a connection. Okay. So the triangles below are similar. Calculate their area. How does the ratio of their side lengths compare to the ratios of their areas? So again, triangles, we're looking for base and height. We're looking for that perpendicular. So the bigger triangle has an area of 1/2 times 9 times 24. Half of 24 is 12. And then 9 times 12 is 108. We'll just say square centimeters. The smaller triangle has an area of 1/2 3 times 8, which is 12 square centimeters. So the ratio of their sides, big to small. So if we think of like the ratio of 9:3, that's a 3:1 ratio. Or 24:8 is also 3:1. So it's a 3:1 ratio. The ratio of their areas is 108:12. And right now that might not look like anything, but if we simplify that, that's going to be a 9:1 ratio. So sides 3:1, areas 9:1. Let's try one more, and then we'll develop a conjecture. So circles are fun because all circles are similar. It doesn't matter. All spheres are also similar. It doesn't matter like other shapes, like not all triangles are similar, not even all right triangles are similar, not all isosceles right triangles are similar, but all, actually all isosceles right triangles are similar. That's true. Not all isosceles triangles are similar, but all circles are similar. So looking at our circles over here, circle 1 has an area of pi r squared, which is 9 pi. Circle 2 has an area also of pi r squared, but this time the radius is 2. So the sides have a ratio of 3:2. This radius is 3, this radius is 2. There's no way to simplify that. And the areas have a ratio of 9 pi to 4 pi, the pi's will simplify out. So then that's just a ratio of 9 to 4. Okay, so now let's see, can we find a pattern? 3 to 1, 9 to 1, 3 to 2, 9 to 4. What is happening to the numbers? Well, it turns out that we are squaring them. So 3 squared is 9, 1 squared is 1. 3 squared is 9, 2 squared is 4. So our conjecture is if corresponding side lengths from two similar polygons, or if the radii of two circles compare in the ratio of m to n, then their areas compare in the ratio m squared to n squared. So again, our m to n was, for example, 3 to 2. That was our m and our n. And then m squared would be 3 squared, which would be 9. And n squared was 2 squared, which is 4. So this is the sides, so then this would be the areas. The cool thing about this is you can apply this conjecture to then find missing areas without having to know all the dimensions of the actual shape. Let's see how that's going to look in these examples. Oh, and this conjecture is also true for surface area. Again, what we want to think of is basically we're multiplying all the dimensions by the scale factor. And so what that means is as we multiply those dimensions again for the area, because an area is a multiplication of two dimensions, what's happening is you're multiplying that scale factor by itself, right? And that's why we get that squared. Okay, so for this first example, we know the triangles are similar, and we know the area of the big triangle. So our question mark is, what is the area of the small triangle? So again, ordinarily, just looking at this, we don't have enough information to find this area. If this is our base, then we would have to have a height, and we don't. So the only thing we can go on is what's happening with the areas here. So here's how I recommend setting things up. So we are going to look at the side ratio first, and then we're going to convert that into the area ratio, and then we'll use the area ratio to find the missing measurement. So if the side ratio is 5 to 3, and it doesn't really matter which ratio you start with, right? If you start with this triangle on top and then this triangle on top, when you do the area ratio, you just have to make sure you're consistent. Bigger triangle over smaller. Or you could do 3 to 5. So to go from the side ratio to the area ratio, we want to apply our conjecture, which tells us to square. So 5 squared to 3 squared is 25 to 9. So that means the area ratio of the big triangle to the small triangle is 25 to 9. So then how does that look for finding it? So this area, remember this is the big. So our area ratio is 25 to 9. Our big triangle has an area of 15, and our small triangle has an area of x. So notice how this area isn't actually a multiplier of 25. Like it's not like a multiple or a factor of anything. That's okay. We just need to know the area ratio. So then we're going to use our cross products. It gives us 25x equals, let me do some mental math here. 135. And then we're going to divide by 25 on both sides. I apologize if you can hear the garbage truck in the background. And that is going to be an area of 5.4 square centimeters. And again, does that make sense, right? Is the area smaller? Yes. It's smaller by about 3. It's hard to see because this ratio is 5 to 3, so it's not as an obvious of a scale factor as like a 2-to-1 scale factor. Okay, let's apply this to the circles. So again, all circles are similar. In this problem, okay, again, I apologize for the garbage trucks. In this problem, I'm giving you the area ratios, and we're looking for a radius. So, we know the area ratios, and again, this is small to big. To get the side ratios, we need to square root. So we need to go from 4 to 9, and then we need to square root each of those dimensions. The square root of 4 is 2, the square root of 9 is 3. So now our side ratio of the smaller circle to the bigger circle is 2 to 3. Now we can apply that to our circles. So 2 to 3, small to big is A, small to 6, big. And now we can cross multiply. 3A is 12, divided by 3, and A is 4 centimeters. And if you just wanted to check your answer, you could go ahead and find the area. So if this is 4, pi r squared would be 16 pi as an area. This would be pi r squared. This would be 36 pi as an area. And if you just wanted to take a peek at what 16 over 36 is, your pi's would simplify. 16 divided by 4 is 4, 36 divided by 4 is 9, and look at that, that ratio is 4 to 9. So that's a way that you could just check your answer. So those are the area ratios. The next second video, we'll take a look at the volume ratios.